Hello everybody. Today we are going to continue our discussion of chapter 2. Today we are going to derive what are known as the kinematics equations. The kinematics equations apply to objects that are experiencing uniform constant acceleration. So like the cruise control is on or a brake is uniformly applied until you come to a complete stop. All right, so we already have in our toolkit that acceleration is equal to the change in velocity per change in time. And velocity, like acceleration, is a vector. We could rewrite this as final velocity minus initial velocity over the change in time. All right, so kinematics equations are particularly useful for helping us find quantities in real life. Maybe you work for an airline company and you know how fast an airplane is going to be approaching the runway, and you know that it needs to come to a complete stop. So your task is to figure out how long must the runway be in order for the airplane to come to a successful stop. Maybe you are a crime scene investigator and you're investigating a crash, and you have skid marks on the road that tell you how far the car traveled, and you know that it came to rest, so how fast was the vehicle traveling when the crash began. All right, so these are a series of equations that use what we already know and help us solve for those variables in a more convenient fashion. So the first thing that we are going to do is we are going to derive equation 1, and we are going to use this first equation about acceleration, and we're going to try to rearrange it to solve for final velocity. So we know that acceleration is equal to final velocity minus initial velocity all over the change in time. So if we want to solve for final velocity, we must begin isolating the variables. So the first thing we need to undo is the dividing by the change in time. And the opposite of dividing is to multiply. So this is now going to give us that acceleration times the change in time is equal to final velocity minus initial velocity. So if we want to get final velocity by itself, we have to add initial velocity to each side, and our final equation, once we clean it up, becomes final velocity is equal to initial velocity plus acceleration times the change in time. That is equation 1 for kinematics equations. All right, the next thing that you frequently want to solve for in kinematics is how far does an object travel? You might not need to know how fast it's going at the end, but you need to know how far it's going to travel. So that's our next goal. All right, so for this, we are going to begin with the concept that average velocity is equal to the change in displacement per change in time. And displacement and velocity are both vectors. Now, when you learn how to calculate averages in math class, you're typically taught to add up the values and divide by the total number of values. So we could also say that average velocity is equal to final velocity plus initial velocity, all divided by 2. You add the two values together, divide by 2. Now, if these both equal average velocity, we ought to be able to set them equal to one another. So we could say that displacement over the change in time is equal to initial velocity plus final velocity divided by 2. Now, we said our goal is to solve for displacement. So if we wanted to solve for displacement, we need to multiply both sides by delta t. All right, and I am going to go ahead and kind of clean this up a bit here. So I'm going to rearrange this and say that displacement is equal to, I'm going to pull that divided by 2 out as a 1/2. So 1/2 times the quantity, initial velocity plus final velocity, all times the change in time. Now, this would be good, but every time that you can eliminate a variable, because we've got displacement, initial velocity, final velocity, and time, is useful. So you might not intuitively think of this, but our first kinematics equation solved for final velocity. So if we put that in place of final velocity, that would give us the equation that says displacement is equal to 1/2 times the quantity, initial velocity, plus initial velocity plus acceleration times the change in time, because our first kinematics equation said that's the same thing as final velocity. Now we can combine like terms. So this now can say displacement equals 1/2 times twice the initial velocity vector plus acceleration times time, quantity times time. All right, now we just got some cleaning up to do. It kind of is like cleaning your room. It's gonna look worse before it looks better. So let's distribute this 1/2 first across the quantity. 1/2 times 2 gives me 1. So that leaves me with 1 initial velocity plus 1/2 acceleration. Oh, acceleration is a vector, times the change in time, end of quantity times the change in time. Now we just need to distribute the change in time across the equation. When we do that, we're going to end up with the equation displacement equals initial velocity times the change in time plus 1/2 times the acceleration. Whoops, that's a terrible vector. Here, let me fix that. Acceleration times the change in time squared. Don't forget the squared, that's super important. This is kinematics equation 2. It would be really useful if you were trying to find the displacement of an object and if you didn't know the final speed. All right, but in real life, we don't walk around timing everything and with a stopwatch. So can we come up with a third equation that does not involve time? We certainly can. And where we're gonna start is actually right here with that equation, right? So I'm gonna rewrite that equation. That equation says that displacement is equal to 1/2 times the quantity final velocity plus initial velocity times the change in time. We said we want to get rid of time though, so we're going to go back to our first kinematics equation, which said final velocity equals initial velocity plus acceleration times change in time. Got to get my vectors here. Sorry, forgot those. And I want to rearrange this to solve for time. I feel like we've done a lot of that already. So I'm going to just go on ahead and say that if we rearrange this for time, the change in time is going to be equal to final velocity minus initial velocity over acceleration. All right, so we can substitute this in for time in our yellow equation. So that's going to give me displacement equals 1/2 times the quantity, final velocity plus initial velocity, times the quantity, final velocity minus initial velocity, all over acceleration, because that's the same thing as time. All right, so what I'm gonna do is I am going to distribute this 1/2 and kind of clean it up. So if we do that, this is gonna look like the quantity final velocity minus initial velocity times the quantity final velocity minus initial velocity, all over 2a, because I took that 1/2 and distributed it, and I've got acceleration down here. All right, now this right here, quantity times another quantity, means we can FOIL, multiply your first numbers, then add on the outside, the inside, and the last. All right, because we've done a lot of math, I'm gonna go on ahead and do that for you and say, when we FOIL, you end up getting that the displacement is equal to final velocity, oh, sorry, hold on, my bad. That is not displacement squared, sorry. The displacement is equal to final velocity squared minus initial velocity squared all over twice the acceleration. That is an absolutely true mathematical statement, but generally we don't like to have fractions in our equation if we can avoid them. So frequently we rewrite this equation to say final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. And that is kinematics equation 3, which would be useful if you did not know a value of time. So I'm going to post a set of sample problems that help you to practice this. And my biggest tips are write down what you're given in the problem and label it. Don't just put 0 meters per second, 4 seconds, 13 meters per second squared. I want you to label initial velocity is 0, time is 13 seconds, or whatever it is. That way you know what you're working with. Then list what you don't know, what you're trying to find. And then you've got to ask yourself, which of the kinematics equations makes sense for that set of information? If you don't have a time value, equation 3 will be helpful. If you do not have a final velocity, equation 2 is probably what you're going to use. If you do not have any information about displacement, equation 1 is probably your best bet. The other piece of advice I would give you is always reconcile your units. You cannot combine miles per hour with seconds or meters per second squared. You must reconcile those before you plug them in.